Good morning, boys and girls, and we're back again today to talk about definite integrals. So first we're going to do a little reviewing here. Derivative. When we're talking about the derivative, right, these are some things that should go through your mind. Derivative is the slope of the tangent line, or we also refer to it as the slope of the graph. Or just basically, when you hear the word derivative, you should be thinking slope, right? Slope of the function, slope of the graph, slope of the tangent line. Derivative is slope, right? Then, yesterday we talked about indefinite integral. When you see indefinite integral, the indefinite integral is a family of graphs. You had that plus C on the end, which could shift a set of graphs up or down vertically, and so when you take the indefinite integral of something, if you take the antiderivative of something, you just get a family of graphs. Today, we're going to start talking about definite integrals. A definite integral is when I have an integral from 3 to 7 of some function of f of x. When I put limits on my integral, that makes it a definite integral versus an indefinite integral. And what we're now talking about with a definite integral is the area under the curve from x is 3 to x is 7. Or, for instance, maybe something a little bit better here. If I looked at the integral, something we talked about yesterday, or a couple days ago, the integral from 0 to 2 of x squared dx. This is the area under the curve from 0 to 2 of the function x squared. Okay, remember when we started with our Riemann sums, we talked about this area that was underneath the curve. That is what this expression represents. All right, so when you see a definite integral, think area under the curve. All right, with that being said now then, we said the way that we can find this, or a good way to do this, would be to, use a bunch of rectangles to approximate it, and we did that with our Riemann sums, right? Now, if I wanted my approximation to be better than that, what could we do? Well, I guess we could use, more colors. I could use more, and if I use more rectangles, still I get an approximation over approximation, but that'd be a lot better of an approximation. And then so now let's say could I use an infinite number of rectangles? If I increased and made those, those widths smaller and smaller and smaller and put an infinite number inside of there, now I guess that would put me right on the money. So, kind of like we did with our definition of derivative, where we looked at the limit as, those 2 points for the slope of the secant line came together. We're going to do the same thing here. Basically, when I give you the definition of a definite integral, we're going to look at making an infinite number of rectangles to approximate the area under the curve. Okay, so here are 2 limit definitions. Again, we said everything in calculus is going to go back to limits, right? Everything in calculus goes back to our limit definition of stuff. So here's our limit definition of a definite integral. And again, just like with derivatives, we had multiple ways to kind of define it with the limit. Same thing with integrals. I've got 2 limit definitions. So the first one here I have in blue. It says the limit as delta x approaches 0 of the sum, the summation notation, hopefully you remember from trig pre-calc, as from I to 1 to n of f of x sub I times delta x, and that is our definite integral of a to b of f of x dx. Okay? Kind of a very mathy bunch of way of saying this. If we look at the blue picture, again, we have our curve, whatever curve we're talking about, and I've got some rectangles on it. This f of x sub I times delta x is just base times height of the rectangles. Remember, to get the height of our rectangles when we did Riemann sums, we had to plug into the function. So this is just basically the height. That's my height. And this is just the base. And so what we're saying is we're going to take the limit as that delta x, as that base goes to 0. If I shrink that base down to nothing, then I should get an infinite number of, rectangles in on my interval from a to b. Okay? So that is the first definition, limit definition, that kind of accomplishes this fact. Another way of saying this and doing this is the second definition, and just like the first definition, this is just the height, and this is just the base. But now what we're saying with the second definition is to get that base, to get the base of these rectangles, we said what you want to do is take your entire distance here from A to B, and you would divide by the number of rectangles you want to put there to get the base of each rectangle. So B minus A gives me that entire distance, and then if I divide by n rectangles, that would give me the, the base of each rectangle. Okay? But what we're going to do is we're going to take the sum of these, and again, that was the sum of all those rectangles before. We're going to take the sum of this as we send that n to infinity. Okay? The limit as n goes to infinity, the summation of I is 1 to n, as n goes to infinity, of f of x sub I times that base. So just another kind of confusing way. I know when you look at it, it's confusing. But mathematically, another way of just saying that this is the area under the curve when we get as many rectangles as possible. As we take that number to infinity, whereas I shrink the base to 0. Okay? I will show you, they don't get as after this on the AP exam as far as the limit definition as they do with derivatives. But we will do in class. We'll do one example so you can kind of see how this works. I think the important piece of this, though, is just remember that this is just base times height of these rectangles. And if you can get that part down, I think a lot of times it becomes easy then to figure out which is the limit definition that we're dealing with. Okay, now another important piece of this is when we're talking about the area under the curve of some function f of x. Okay, when f of x is above the x-axis, that area is considered positive. When f of x is below the x-axis, that area is considered negative. Okay, so if I were to look at the integral from a to c of f of x, that would be a positive 4. If I were to look at the integral from c to d of f of x, that area would be negative 3 because it's below the x-axis. Okay? If I'm going to look at the area from a to b on this of f of x, when we talk about this, this is the net area. It is not the total area, but is the net area. So to find this, I would have a positive 4 plus a negative 3 plus a positive 2, or this integral, the net area, would be 3. Okay? So when we're looking at a definite integral, you're looking at the net area under the curve, not the total area under the curve. So be careful the difference between those two things, and be careful if they're asking about the net versus the total area. If I wanted the total area under the curve here, you would still say that the total area is 9. However, the integral from a to b is the net area, and that is 3. Okay, next is theorem 5.5. Continuity, holy moly, struggled with that word, implies integratability. Continuity implies integratability. I laughed at this whole thing because as I was doing my notes, integratability, I don't believe is a word, which made me think, did I create this theorem? So then I went back in the book to try to find theorem 5.5, couldn't find it, so that's what I'm saying, Mortara's theorem? I don't know. And then if you look at it, it totally sounds like just something I would say. If f of x is continuous, then you can integrate it. That doesn't seem very mathematical, so I think this is Mortara's theorem. Okay? But this is something that's totally true and that we need to be aware of. Just because in order for us to integrate a function, it just has to be continuous. Okay? If it's continuous, I can integrate it. It's not a function that has to be differentiable. Okay? An example of this would be absolute value. Absolute value is not differentiable. It's got a pointy part of the graph, right? However, it's continuous, and that's really all I need, because if I was going to try to do this, I could find the area under the curve from A to B. So I could integrate this. Some functions you're just going to integrate, and maybe you can't do it algebraically, but I totally can do it graphically through the function. I could find the area of those triangles. Okay? So in order for us to be able to integrate something, it just has to be continuous. You just got to be able to find the area of the curve. It does not need to be a function that is necessarily differentiable or integratable. Again, I'm not sure if that's a word. All right? Let's all celebrate Mortara's theorem. Yay! Okay, so here are some quick properties that you need to be aware of. If you have a definite integral that goes from A to A, that starts and stops at the same spot, then that's going to be 0, because there is no area from the curve where you're starting and stopping at the same spot. If your limits are flipped, if you're going from B to A instead of A to B, in order to flip those limits, what you can do is you can just put a negative in front. Okay? If I'm going from left to right instead of right to left, right to left instead of left to right, that just makes our area negative if we're just going backwards. Okay, so you can flip your limits by putting a negative in front, is the moral of that story. If I have an integral from a to b, that'd be equal of the two integrals from a to c and c to b, where c is some other value, that is there. If I split up some area and I go from, if I do a quick little picture, the best maybe, a, if I go from, a to c and then c to b, if I add those together, that's going to give me the area from a to b. And you can have a bunch of other pictures, but that's the general idea. Okay? The next one, if you have a constant k, you can pull that constant out in front of your integral, and it doesn't change anything. Okay, just like you can pull it out from a limit, and that's why, again, these are limit-based. And then the last but not least, if I'm taking the derivative of, a couple of terms or functions, really, what I can do then is I can split up and I can take the integral of both those things separately, and put the plus or minus sign between these integrals individually. Okay, so some quick properties for you to be aware of and know how to use, and we'll see how those pop up here in a second. Okay, for our first example here, we want to find the area under the curve of the function from 0 to 4. So first thing I do is sketch a picture. Okay, so this is a parabola that opens down, would look something kind of like that. We're trying to approximate the definite integral 0 to 4 of 8 minus 2x squared dx. Our issue right now is we don't know how to solve this algebraically yet, and again, I know if you're in physics, you might be doing some of this, but I'm going to say right now, we still cannot use, that's the fundamental theorem of calculus, and we have not covered that yet, so don't use it. We need to approximate this using Riemann sums, so that's what we're going to do. We're going to use a left Riemann sum, or left RAM. All right, the book says we want to do a left RAM with n equaling 4, meaning I want 4 rectangles. So I drew my 4 rectangles. Again, I want the upper left-hand corner on this, or, again, it drops below the x-axis, so then it'd be the lower left-hand corner on the graph. So this is what the rectangles would look like. Now I just need to approximate the area of all 4 rectangles. Okay, so to find the area, we would do the base times height of these rectangles. So my base in all these is 1, since I have 4 rectangles in the interval from 0 to 4. And then I would need to find the heights at that left point. So at f of 0, f of 1, f of 2, and f of 3. At f of 0, I get 8. When I plug 0 into the function, again, I can't estimate this stuff. I actually got to go and find it. When I plug in 2, or when I plug in 1, I get 6. When I plug in 2, I get 0. And again, that's why there was like really no rectangle there. And then when I plug in 3, I got negative 10. I factored out my base of 1, or you could have had 1 times all that stuff still. And when we put this together, though, we get our approximated area is about 4. So using a left Riemann sum approximation, this integral would be about 4 if we were to work it out. All right, so next problem here. We want to evaluate this integral, negative 4 to 2 of 2x plus 4 dx. Again, we don't have the tool to do it algebraically yet. Again, we're doing all this stuff where we're going to doing it graphically and geometrically. Okay, so the first thing I'm going to want to do is I'm going to draw this picture out. All right, so we have a line with a y-intercept of 4 and a slope of 2. And we are trying to find the area under the curve from negative 4 to positive 2. And so again, this is the net area. But I'm going to go find the areas of these triangles and find the net area between the two, and that would give me my integral. All right, so for the first triangle here, area of the triangle is 1/2 base times height. So 1/2 the base is 2 and the height is negative 4. And I tend to make that height negative. That's how I keep track of my area being negative, is by adjusting the height being negative. And then the other triangle, this big triangle, is 1/2 the base is 4 and the height is 8. Now we can put this together to get 12. So this integral is about 12. Done completely with geometry, and that's again the way we need to do these tonight. Okay, with our last little bit here, we're given a couple of integrals. The integral from 1 to 4 of f of x dx is 8, and the integral from 1 to 6 of f of x dx is 5. I want to evaluate the integral from 1 to 4 of 3 f of x dx. So here we're just going to use some of our properties. I could rewrite this integral as 3 times integral 1 to 4 of f of x dx using our constant property. And so I know that this is 3, and we are told up here that that integral is 8. So this is going to be 24 if I evaluate it. Same, if I wanted to find the integral from 4 to 6 of f of x dx, I could use some of my properties. I could say that the integral from 1 to 6 of f of x dx is equal to the integral from 1 to 4 of f of x dx plus the integral from 4 to 6 f of x dx, splitting that one up in the middle. And now I can plug in for the 2 that I know and solve for the 1 that I need. So the first one is 5, and the second one is 8, and then I subtract and solve, and I get that my integral is equal to negative 3. All right, boys and girls, that concludes today. Go get after it. Have some fun.